Okay, today we're going to start talking about chemical bonding. But before that, we need to get into ions. And so we're going to talk about what ions are and how you make them. So to start with, ions are going to be a charged atom. So up until now, when we talked about like the Bohr diagram or those Lewis structures, we've been really focusing on neutral elements, neutral atoms. They've had the same number of electrons and protons. But what we're going to talk about today is that you can take that neutral atom and either add electrons or remove electrons because of that shell. And so when you remove electrons, take them away, you're going to make a positively charged atom, well, or ion now. And if you add electrons, you're going to make a negatively charged. All right, so let's take a look at how this works. Well, the formation of what's called a cation, which is the name for a positively charged ion. So if that atom loses electrons, it's going to become positively charged. And so the reason is fairly simple. All right, when we have this atom here with the same number of positive protons as negative electrons, and then we take away an electron, the protons, the positive parts, remain the same, while those electrons become less. So since we are taking away a negative, we then see an element become positive, all right, because we're subtracting a negative. And then similarly, if we see the exact opposite with what's called an anion or a negative ion, that if an atom gains electrons, so we started with the same number of protons and electrons, but then we gain an electron, we now have more negative electrons than positive protons, and so we have this negative charge. All right, so cations are positive ions, anions are negative ions. The same way when we talk about like a cathode or an anode with electrical, that's where that comes from. And so we're going to refer to, well, why? Why does this occur? And that's because we have this octet rule, where all atoms want to have the same electron configuration as a noble gas. And so if you have something like oxygen, it wants to become neon, or it wants to have the same electron configuration, because when we look at those, the shells and the orbitals, everybody wants to have filled orbitals in that p. They want to end on a p6, right? And so atoms want to achieve the electron configuration of that noble gas. And so they can do it in two ways. They can either gain electrons to fill it out, or they can remove electrons to go down to it. And so atoms of metals are going to tend to lose those electrons, which will end up leaving them with a full subshell. And so what we mean by this is, if we were to take, a simple Bohr diagram, and we're to say, well, we have, what's going on here with this pen? I don't know what's going on. Let's see. Hold on. Let's erase that and start over. Okay, so we're starting out with this inner circle, right? And we're to put 2 electrons on it. And then we're going to go to our next one here. And I know that's a sloppy circle, but it just has 1. What can happen is, if this 1 leaves, right, and we'll talk about where it goes, what ends up happening is that shell on the outside kind of just goes away. It's there, but now it's not occupied. Remember, that valence shell wants to be occupied. And so then this will fall to that next lowest level, which now is full. That's helium, a noble gas. All right, so when we talk about here, right, it leaves a full octet in the next lowest energy level. All right, so if it's this here, lithium, and it loses that 1, it gets that electron configuration of helium. All right, now in our nonmetals, they're going to gain electrons to go up to the next, to fill that outer shell. So if you had instead something like fluorine, which has the 2 in the middle. And then fluorine has 7, right? We have 1, 2, 3, 4, 5, 6, 7. It's going to want to have one come in. It's going to want to gain an electron to then become 8 full. All right. And it takes on that full octet on the outside. All right. And so that's our noble gases. All right. They have that full octet. All right. So how do we know if it gains an electron, loses? Like we said, metals tend to lose, non-metals tend to gain. Well, it's because of this thing that we can measure called ionization energy, which is going to be the energy required to remove an electron, from that atom. And so we're going to look at that third group, right? Sodium, magnesium, third period. Sodium, magnesium, aluminum, silicon. And so this is the ionization energy, the energy to remove one electron. And then it goes down, it tells us, well, this is the energy to remove a second, a third, a fourth. We can ignore that stuff down there. We want to focus on this very first line, the first ionization energy, the energy to remove the first electron. And so what we can see is sodium is relatively low, 496. And then it goes up in magnesium. And as you go across all the way to argon, look how high that number becomes. So removing an electron becomes harder and harder as you go across. And so what this thing wants to do in sodium, magnesium, aluminum are metals. These have low energies. They want to give away that electron. But when you come over to the nonmetals, phosphorus, sulfur, chlorine, they have that high ionization energy. They don't. It takes too much energy to give electrons away. They instead want to bring the electrons in. They want to gain them. And so we establish, using the periodic table, a trend for ionization energy. It increases from bottom to top and left to right. All right, so our ionization energy will be highest up here near helium, lowest down here near francium. And so what we're going to notice here then is this is the exact opposite of atomic size. And so why is that? Why is it that ionization energy, the energy necessary to pluck that electron off, is the exact opposite of size? And when you think about this, it makes sense, because the closer those electrons are to that positive nucleus, the tighter they're going to be attracted to that nucleus. The further away, the more distance there is, the less. That's Coulomb's law, right? Coulomb's law, you have that electron has the same charge, that nucleus has the same charge, but the further away it goes, the easier it is to pluck it off. That force of attraction's lower when that distance goes up, that R, right? We have our Coulomb's law, we know that, which we have, if I can get my pencil up, which we have here being that, force is proportionate with Q1, the charge of one, over Q2, the charge of the other, divided by R. And so if the charges are remaining the same and that R is getting bigger, we have an easier way. Or when you have that nucleus and you have these rings, the more rings you have, the easier it's going to be to pluck that electron off. The further away it is as you go out there, right? The easier it is to just pluck that thing off. And so that's the ionization energy. It explains, why these elements either want to gain or want to lose. And so the last thing that we're going to talk about is that when atoms gain or lose these electrons, their electron configurations are also going to change. And so when we look at something like oxygen here, which has 8 electrons, all right, and we go to do our electron configuration, well, when it has a -2 charge, it's now gained 2. Instead of 8, it now has those 10. So instead of being its normal 1s2, 2s2, 2p, 2p4. What it normally is with 8, it's not going to be that. It's going to be 1s2, 2s2, 2p6. It's gained 2 electrons. And so we have that. Aluminum normally has 13 electrons. It normally has a 1s2, 2s2, 2p6, 3s2, and a 3p1. But that's not true anymore. When it has a positive 3 charge, it's going to lose 3. So it loses that one there and those 2, meaning it also becomes 1s2, 2s2, 2p6. That's the electron configuration of a noble gas, that it ends in that 2p6. And coincidentally, look at this, they're the same, right? These are the same electron configuration. Now remember, they're not going to become the same element because this nucleus still only has in it 8 protons, and this nucleus still has 13 protons. But the electron configuration, what's going on in those clouds and orbitals, is the same. And so what we call this is an isoelectronic series. Isoelectronic series, which is a series of elements or atoms that have the same electron configuration, although they do not have the same nuclear charge. And so as you look at this group here, what happens is it's around that neon. You have the three nonmetals before it gain electrons, like fluorine and oxygen and nitrogen. They gain them to become negatively charged, and they end up becoming the same electron configuration, that 1s2, 2s2, 2p6 that we just saw. And so do the metals right above neon, sodium, magnesium, aluminum. They lose those electrons to also have that. And so although the nuclei are different, we can see this is the increasing Z, or the increasing nuclear charge, right? Because you have 7 protons, 8 protons, 9 protons, 10 protons, 11 protons, 12 protons, and 13 protons. So increasing nuclear charge, you have that these things are all going to have that same electron configuration, which is 1s2, 2s2, and 2p6. All right, so this is our general discussion of ions, how they form, why they form, and what happens to their electron configurations.